time we have Sylvain Barbot, who will talk about thermobaric controls of fault friction. Sylvain, the floor is yours.
Yeah, thank you. Okay, welcome back to the seminars. So I will talk about the physics of friction. So first I want to thank the organizers for setting this all together. Okay, maybe the water was too cold. So thank you for setting this all together, and thank you for giving me this opportunity to talk about my work. I've been working in the physics of friction for 5 to 6 years, and so there's been a lot of progress that's been done. It's difficult to summarize in a short time, so I did my best to show you the most salient ingredients. And the motivation for this is of course, that friction is an integral part of every aspect of seismicity. So it's an important underlying physical mechanism that we need to understand if we want to pave the way for earthquake prediction, short-term, long-term. And it's also an area of research, an area of the earthquake science that is very poorly understood. And across various tectonic settings and oceanic transforms, continental crust or subduction megathrusts, we have this depth dependency of the earthquake characteristics with slow slip events and tremors and very large earthquakes occupying different depths of these major plate boundary faults. And so temperature is an important characteristic. Of course, temperature also controls the grade of metamorphism. And so there is a lot of aspects that we need to understand to predict earthquakes. And the angle that I will approach this problem is to try to understand temperature and pressure dependence of the frictional properties of rocks and exploring this dependency for different lithologies. So there's a lot of work that has been done on friction. And so I'm going to integrate the laboratory observations of many different scientists in the last 4 to 5 decades and try to connect the dots and explain these observations relative to each other and build a mathematical model that is as simple as I can make it, but it's still quite complex. So to connect all these observations, and I'm going to try to explain to you how friction works. And I'm going to start simple. So I'm going to describe the fundamental physics of friction in isothermal conditions. So we're not going to look at temperature, but we're going to look at normal stress. Okay? It's an important part of the frictional resistance. Then we're going to add up the thermal activations and look at the temperature dependence of friction. And as we will see, there's different ways that temperature and pressure act on the frictional resistance of rocks. If you change temperature slightly, there is going to be a response to this perturbation. But if you change it a lot, the entire set of frictional properties will evolve. So it's different aspects of frictional dependence that we're going to discuss. And I'm going to discuss then a perfect example of how that plays out at the brittle to flow transition that controls the bottom boundary of the seismogenic zone on faults. And then finally, I'm going to wrap up by describing the thermobaric activation of fault friction, which is the title of the talk. So the temperature controls different transitions of fault stability, but the pressure affects at which temperature that happens. So there is a pressure and temperature dependence of all of these effects. Okay? So we're going to start with fundamental physics of friction. So what is friction, essentially? How does it work, and how can we use it to make predictions about earthquakes? So I'm going to start from very simple. And the first assumption, which I'm going to demonstrate and explains the data, is that frictional resistance is proportional to the actual area of contact between two solids. So if we know the area of contact, we can immediately predict the frictional resistance. So as is often the case in science, if you want to understand something, you need to back out and look at the bigger picture to make some progress. And here, this is to first look at the real area of contact. So I often say this when I grab any solid in my hand, there's only of the order of 1% of my hand that is in true contact with the solid object, because the contact is really supported by microasperities. So that's where all the physics happens. And so there is a lot of theoretical work that describe the nature of this contact and how much area of contact we should expect from the topology of these surfaces. The simplest one is a collection of what we call Hertz contact, after the name of the physicist who described these. These are simple elastic spheres under pressure that are pressed into each other or against a rigid wall. And when you do that, it creates an area of contact that can be resolved analytically. And when that's the case, it's proportional to the normal stress that is applied normal to the interface to the power of 2/3. And then if you make these spheres a little rough with a fractal geometry, the area of contact scales almost linearly with normal stress. It's the power 26 to 27. And if you randomize the initial height at which these spheres are pressed against each other, then the area of contact is linear to normal stress. For a long time, this model has been favored because people looked for linear models, but in reality, as we will see, this is in fact a better representation. So to generalize these different end members, we can define a power law. So the area of contact will be a power law of normal stress to the power 1 minus beta and to the original size of these spheres. And then we can make a second assumption, which is the yield strength, which is closely related to frictional resistance, is proportional to the area of contact. So that's how simple you can make it. Real strength is a scalar times the area of contact. And of course, you have the area of contact, so all of these terms are inherited there. And it turns out there are a few experiments that can validate these two relationships individually. So to convince you of this, we have to go to the engineering literature, where surfaces are actually engineered. So we create surfaces that have the topology that we fully understand, and then we can control it and test these relationships. So this is the case for two papers that I'm going to describe. One has this sort of topology. So on a lens, these investigators have added some microasperities of a fixed diameter, and for this measured the area of contact using light transmissivity. And then after done that, they slid the interface and measured the frictional resistance. Okay? So first, this is the real area of contact as a function of normal stress. This is a log-log relationship. You can see it's a straight line, and that constrains the power exponent beta extremely well to about 0.17. And then in these similar experiments, you can see that if you have a nonlinear relationship between area of contact and normal stress, that means you're going to have a nonlinear relationship between yield strength and normal stress, and that's exactly the case. You can see that the coefficient of friction is a decaying function of normal stress. For decades, we have assumed that the frictional coefficient is not a function of normal stress. This is a mistake. It is always a function of normal stress, and if it isn't, it's because you haven't explored a wide enough range of normal stresses. So another experiment is done on PDMS. This is published in the same year by different investigators, where they measure this time the yield strength as a function of the real area of contact. So this is directly probing this relationship. And you can see the data with brackets and a straight line. It's not even a fit. It's just a straight line. And you can see it fits the data very well. So the yield strength is a linear function of the area of contact. So that validates that. And then the frictional resistance is a power law of the normal stress, and that validates this relationship as well. So the fundamental pillars of what defines friction can be validated really thoroughly based on very high quality data. So when you define the yield strength proportional to the area of contact, it provides a rate-independent failure criterion. And that's not sufficient to characterize earthquakes, because we know from the spectrum of fault slip that we can have slow slip, slow earthquakes, fast earthquakes, different types of rupture propagation. And so the velocity of sliding is quite important. And so we need to define a rate-dependent failure criterion. And so that will be this power law relationship that says that the velocity of sliding is proportional to the shear stress to a power. And this shear stress is relative to the yield strength. Okay? So we inherit everything that we have discussed into a rate-dependent rheology. So when we combined what is the yield strength as a function of area, and what is the area as a function of normal stress and size of microasperities, we obtained constitutive friction law that is strain rate, state, and normal stress dependent. Okay? And the reference friction coefficient simply incorporates the ratio of material properties. Okay, so with this, we obtain a fundamental law that describes the frictional resistance of rocks. But this is formulated in a different way. Instead of what is the frictional resistance as a function of velocity, it says, well, the velocity of sliding can be predicted based on everything else. Okay, so this is a constitutive law. For any given condition, it predicts the velocity of sliding, which is really what we care about. But we can flip this around and describe a friction coefficient. So we simply have to invert that relationship. So it looks like this. Friction coefficient is a reference value modulated by dynamic variables. So all of this is raised to a small power, 1 over n, or alpha, or beta. So in some cases, it can be neglected. If you neglect this, you get the yield strength is mu naught sigma, which is the Coulomb failure criterion that was imagined in the 19th century, and in fact before in the 18th century. So using these very simple assumptions, we can explain sort of simplified failure criterion that was put together a few centuries ago. But the physics of this describes a nonlinear relationship between shear stress and normal stress. And this simple failure criterion is simply a local approximation when the effect of all the other dynamic variables have been neglected. And we don't want to do that. We want to keep them. The second thing that is fundamental about friction is that it is sort of time dependent. So if you want to slide two surfaces, it's easier to do it immediately after they are in contact than, say, 2 hours after they've been sitting together and sort of adding cohesion between the two solids. And that has been really clearly illustrated by the experiments of Dietrich and Kilgore in 1994 and 1996, who image the microasperities. You see, this is 100 micrometers at the interface between two transparent materials, and after 1 second, 100 seconds, or 10,000 seconds, you can see these microasperities growing and flattening. So they collapse under their own weight, if you will, right? They are subjected to normal stress, so that provides a driving force or a source of energy, and these microasperities slowly deform, slowly collapse. And as they increase the area, it increases the frictional resistance once you start sliding them again. So to understand earthquakes, we need to capture this phenomenon. So since there is creep at microasperities, you can employ a power law, a creep law, that is stress dependent to a power and microasperity size dependent to a power to describe this flattening. It's called compaction creep. You can also approximate the strain rate of compaction by the normalized change of this size of contact. Now, so that describes the compaction. And of course, we also want to bring in sliding. And when you slide, all of these microasperities, they are going to find a new neighbor. And that's a random process, random in the sense that it depends on topology, which is always different and evolving. So for this, we describe a random rejuvenation process where the size of microasperity is going to follow a decaying exponential of slip, of cumulative slip. So the more you slip, the more you randomly repopulate your contacts, and they start small. So you can use that or take the differential equivalent, and then to build an evolution law for these processes, you have to add up this term and that one So one is a healing process, the other is a weakening process, and that gives you this. This is an evolution law that combines compaction creep and rejuvenation by random redistribution of contacts. So you can take the difference between these two, this term minus that term, and that gives you an evolution law that is fundamentally compatible with the aging law described by Ruina in 1983. Or you can take the log of the ratio, and that's a perfectly valid way of looking at the difference between two positive quantities. And if you do that, that gives you the sleep law, also derived by Ruina in 1983. Regardless of these two end members, you get a steady state size of microasperities that is exactly the same, and is an inverse function of velocity and a power law of normal stress. And that means that normal stress will play a key role in the steady state strength of frictional contacts. So we can also validate this relationship. So now we have different ways to describe friction by the area of contact or the frictional resistance directly. But we have an evolution law that makes all of these things a function of velocity and normal stress and so on and so forth. But there is a lot of data that we can use to constrain this. One of the best is also from Dietrich and Kilgore. They measure the area of contact as a function of normal stress for 4 different materials, 2 of which being rocks, quartz and calcite. But in velocity step experiments, they also measure the friction coefficient. So now it's not the static friction, it's an evolving frictional properties. And the black is the data. So anytime you change velocity, there is a direct effect and an evolutionary phase, direct effect, evolutionary phase, etc. And simultaneously, they measure the area of contact because all these materials are transparent. So this is based on optical transmissivity across the interface. And the area of contact is inversely proportional to the sliding velocity. So we can, with one consistent set of experiments, validate 3 different equations from the constitutive model. So we can explain at first order the evolution of the area of contact, the fold strength, and the area of contact as a function of normal stress. So this principle of modulating the area of contact during the seismic cycle has been used in the last 2 or 3 decades to image seismic ruptures in real time. Jay Finberg has been championing, and his students and postdocs have been championing these observations in the lab, which can be illustrated by this type of results. This is from Serlitsky, published a few years ago, but it's representative of their work for a number of years, where they look at, oh, it's right there, they look at 2 blocks moving past each other, and it's in plexiglass, so you can see through, and light can be reflected or refracted or transmitted across. So the amount of light that makes it through the interface is a proxy for whether the interface has moved or not. And so as a function of distance and time, you can see more and more area that has reduced area of contact. And so that means that's a proxy for the passage of the seismic front, the rupture front. And so that allows us to measure the rupture speed and other characteristics. So if you combine all the elements that I've described, the area of contact, the frictional resistance, and the evolution law, you can in fact reproduce these observations in numerical models that describe the evolution of the real area of contact during the seismic cycle. So empirical friction laws or linear elastic fraction mechanics can describe such phenomena. They can describe the mechanics of this fairly well. But none of these frameworks can tell you how much light goes through the interface. Okay? So for this, you need physics. And this is one of the many things that using a model for friction really adds. So in this case, we simply assume that the light transmissivity is proportional to the real area of contact. Now, I told you that the steady state size of microasperities that modulates the area of contact and modulates frictional resistance is a function of normal stress. And so at steady state, and at a fixed velocity, the friction coefficient is a very strong function of normal stress. And it seems simple to just say that, but it goes contrary to everything that people have said in decades. So I want to make this strong, that this friction is a strong function of normal stress. And this is often ignored. I'm going to give you a lot of evidence for that from the lab, okay? So this is, I don't know how many rocks, 10 or so, as a function of normal stress, a small range, 7 MPa, an enormous range, 700 MPa, 60, right? A lot of sedimentary rocks, volcanic rocks, and carbonates. And in all cases, the friction coefficient is a decaying function of normal stress, okay? And it's unbounded. You can have infinite friction coefficient. There's no limit to how high it can be at vanishing normal stress. The strength, though, is finite because the strength is not the friction coefficient. It's the friction coefficient times the normal stress, which goes to 0. And so this is basically the universal behavior of virtually all rocks. They have a friction coefficient that goes to infinity at vanishing normal stress. But there are some important class of rocks that do the opposite. They still depend on normal stress, but in the opposite way. And that's the phyllosilicates or the sheet silicates. And they are very specific in the sense that they have a polymer type structure that repeats, forming two-dimensional sheets. And so typically, one of this what we call the interlayer between two sheets is electrically charged, and that attracts electrically charged water. Water is a polarized molecule. And so you have osmotic pressure that forms at the interlayer, in the interlayer space. And so it's a very specific condition. And you can actually understand this by understanding that this layer of water in the interlayer space can actually separate the sheets of silicates and reduce the area of contact. So the area of contact is inversely proportional to the pore fluid pressure. And we understand from theoretical models of osmotic pressure that the pore fluid pressure is also fighting against normal stress. And so if you put these things together, it changes the area of contact as a function of normal stress by adding a power exponent of 1. So there is an additional relationship with normal stress. When you do that, then you have this 1 that comes in at steady state, and it flips the relationship of the friction coefficient from being a decaying function of normal stress to a growing function of normal stress. And that's what we see for a wide collection of different sheet silicates, talc, some serpentinites, muscovite, morillonite, etc. So it's widely observed and often ignored in geophysics, because typically we don't care about rocks. But that's a mistake. So we understand this. So stay away from assuming that friction is independent of normal stress. So now we're going to look at, maybe it basically this covers the underlying physics. If you understand this, you're good to go. But I want to walk you through thermal activation and then thermobaric activation, so we need to march on. So friction is temperature dependent. I've ignored that so far, but it's weakly temperature dependent, at least in appearance. In reality, I will show you that it's strongly a function of temperature, but with two opposing effects that typically cancel each other out. So let me describe this. So first, to describe friction, including the temperature dependence, we simply add an Arrhenius thermal activation. And that typically involves an activation energy, Q, H, something, and an activation temperature. Activation temperature is not very well known. People don't know what it is, but Q over T naught is the change of entropy of the reaction. So you can think of it as change of entropy, activation temperature. These things are related. And so this is still the yield strength modulated by area. The area is modulated by normal stress and other things. And when you combine it together, you get this longer equation. And it's as long as it's going to get. This is a friction law that is slip rate, state, normal stress, and temperature dependent. And so the frictional sliding is thermally activated. And so that means that if you warm up the rocks, it should slide more easily. But it's never really the case. Why is that? Because the compaction creep is also thermally activated. So when you heat up the rocks, they flatten faster, it increases the area of contact faster, and that hardens the rock. And so you have a weakening effect that fights against a hardening effect. So the net effect of temperature would be a combination of these things, and sometimes it's nothing at all, sometimes it's weakly weakening, sometimes weakly strengthening. It depends. And extending the evolution laws for temperature is trivial. You take the creep law that we discussed earlier, which was just these terms, and you add a thermal activation. So there's an activation enthalpy H, activation temperature, and that's it. So you can take the difference between compaction creep and contact rejuvenation, or the log of the ratio, and that gives you the slip law, well, the aging law and the slip law, respectively. So I'm going fast because it's just mechanics. So again, these formulations can be validated by very carefully crafted experiments conducted by Fred Chester in '94, a seminal paper that is not cited enough, so please read it. And in these experiments, in the single run, he changes the velocity, the loading, uniaxial loading in piston. So there's a velocity step. And once he reaches a very low velocity, enforces a temperature step. You can't step temperature, but it cools it down. It goes slowly. So when you plot it as a function of slip, it looks like a step function. And look at that. When you step temperature down, you have a direct effect in an evolutionary phase. And when you step temperature down, you have a direct effect in an evolutionary phase. But they are equal in opposite directions. This is one experiment, this is another, and the model that I described is in red. So we can capture this and notice that the direct effect for temperature and velocity are not the same, and the evolutionary response is not the same either. So these are captured in the model by Q, and the difference between Q and H. Q controls this, Q and H controls that. Okay? So having two different activation energies allow us to fit these experiments. Now, that's not the only thing that temperature does. So if you really perturb temperature like Chester has done, you're going to have the impulse response of the system to temperature changes, or its integral. But when you change the temperature drastically, by hundreds of degrees, then the entire set of frictional properties will be different. The weakening distance, the direct effect, the steady state, everything will be different. Steady state, everything. So there's two different effects with friction, with temperature. There's perturbations and the effect of the bath temperature, like the ambient temperatures. And there are many experiments that document this. This is 6 of them, covering quite a range of temperatures, from almost room temperature to 700 degrees. And you can see 2 different data. The direct effect is A. It's shown in black. That's the jump that I described. This is the direct effect. It's defined like that. Yoshi also explained this earlier. And the steady state response is also the derivative of friction with velocity, but at steady state. So A is independent of temperature for an enormous range of temperatures, but A minus B is not. So you switch behavior when you place these rocks in very different ambient temperatures. So the model that I will describe next is showed with the solid lines, and it captures all of these observations, but I haven't described it yet. So what happens is you have the competition between different healing mechanisms. I discussed that over time you have the creep of microasperities that increases the area of contact, but you can actually collapse these microasperities by different mechanisms. The backup plan is viscoelastic flow in the immediate vicinity of the microasperity, like everything deforms in the bulk. You can also dissolve it by pressure solution creep and precipitate it nearby, thus enlarging the surface area. You can also, in a gouge, you can crack your minerals and increase the area to volume ratio and therefore increase the overall area within the volume. So there's different mechanisms by which you can increase the area. And it doesn't matter which one it is, as long as you increase the area, it's stronger. So to capture this, instead of doing a single creep law, like we had before, we can sum them all up. So if you have 3, 4, 5, 7 different mechanisms, add them up. And they all have a different activation energy, activation temperature, normal stress dependence, sort of grain size dependence. And in many cases, only one will really operate. And the others just need higher temperature to work. But it's OK. One will produce 0 strain rate, and the other 10 to the minus 14 per second. And you just add them all up. And so with this, if you account for different mechanisms acting on different minerals within your interface, you can capture this phenomenon. And once again, you can look at the difference between compaction creep and rejuvenation, or the log of the ratio, which involves this sum, and both formulations work fairly well. And so this effect, we see it in the lab so well. You do a down step from 1 to 0.1 micrometer per second, and this is your frictional resistance. It's kind of the baseline level. And you do it at 100 degrees, you're going to have velocity strengthening. And then you do it at 200, you see velocity neutral. You do it at 300, 5, 6, and you get even some sort of stick-slip instabilities. So the ambient temperature controls the frictional properties. And with these frictional properties, you can then have a direct effect in evolutionary phase. So it's 2 layers of different effects. So that's using the aging law, the sleep law. And in general, it works fairly well. Now, I discussed how different mechanisms can heal the contact, but you also have different mechanisms that break it. And that is what happens at the brittle to flow transition. And so I'm going to convince you from the data that there are multiple mechanisms that allow faults to slide. And it's sort of the same physics. It's just breaking things and moving. But in one direction, you cannot move forever. So that only compaction has to go with pore size reduction or flattening of areas. And at some point, it saturates. You can't just go more than this original thickness. But in the tangential direction, you can do it forever, for hundreds of kilometers. And so because of this difference of topology, you have different mechanisms. And in the lab, we see it so well. I mean, once I explain it to you, you cannot unsee it. So once we know the answer, it's so much simpler. So with 3 different rocks, this is wet olivine, dry olivine, and basalt. And at low temperature and at high temperature. And hold on, I'm going to show it to you. At low temperature, you step the velocity, you have a direct effect and an evolutionary phase. And typically, they have opposite directions. So you go down and up. It's so clear. This is for wet olivine. For dry olivine, you go up and down. It's an up step. And then for basalt, you have a direct effect and then the evolutionary phase, right? So it's definitely rate and state friction. There is a direct effect and an evolution of the state. And then you do it at high temperature, and it's just rate dependent. It's basically a creep test, like viscous flow. So there's no state. So this mechanism is not this mechanism. It's just not the same. It doesn't have the same mechanical response. And so what happens is that across this, we reach the brittle to flow transition. And we switch from a dominantly frictional process, we can call it cataclesis, to a dominantly flow, rate-dependent response. And so if you don't have a theory that accommodates its basic observation, you're not going to capture the bottom of the seismogenic zone and other important aspects of friction. So a physical model of friction that includes all of the seismogenic zone and its boundaries must incorporate multiple deformation mechanisms. And it's also trivial to incorporate. We had a flow law for the tangential sliding, thermally activated. velocity is proportional to stress to a power. Well, there's different ways of doing this. So we're going to sum them all up because they are all strain rates. They're instantaneous, infinitesimal. So you can add them up. And that explains the velocity and temperature dependence of friction very well, because if you have two mechanisms that operate at different sensitivities to shear stress, nature is going to take the path of least resistance, which is another way to say that even at any given shear stress, both mechanisms will act, but one will be so much faster than the other, so the other one can be neglected. And then, so it's going to give you different mechanisms as a function of velocity, and therefore different frictional properties. And then if you change the temperature, one mechanism will be more sensitive than the other to temperature, and it's going to shift where the transition from one mechanism to the other occurs. So that gives you a temperature and velocity dependence of frictional properties. Okay? So that's a sketch. I'm going to show you 3 different data sets that are remarkable in how much of this temperature space and velocity space they cover. So they're kind of unique by their extent. Okay? So the first one was just published a month ago by Huiru Lei at CEA China, where she explored different velocities. Well, that's kind of common. But look at the precision at which she describes the temperature dependence of granite. Okay, these are natural samples from the Anning-He fault in southeastern Tibet. And you can see this transition to a very different A-B, so a very different stability at high temperature, but that transition depends on velocity. Okay? So the transition temperature depends on velocity, and I will tell you how that also depends on pressure in a moment. Okay, and this is from Mike Blampede, who's right there. It's less extent compared to that, but it also describes other parameters fairly well. And this combination is unique, and that constrains the model extremely well, including 3 different stability regimes: strengthening, weakening, strengthening. So that's the top of the seismogenic zone, that's the bottom of the seismogenic zone. They're also describing the steady state friction coefficient. So it originally increases, so there's temperature hardening, and then at some point it weakens a lot, and we call that temperature softening, and that's a behavior that allows thermal instabilities to develop. So it's quite important as well. So that's for granite, 2 different experiments that are quite remarkable, and they describe the frictional properties of a nominal continental crust, except for the fact that the continental crust is typically oceanic in origin in many cases, maybe 50% of them. So it's more complicated than that, but no time for this. This is natural sample from the Alpine Fault in New Zealand. This is quite remarkable. It covers 5 orders of magnitude of slip velocities. So it's easy to do this part. It takes a few seconds, but it takes 150 hours to do this one. All right. So you have to imagine the patience and also this instrument being extremely reliable to deliver quality data over extended periods. And that has a function of temperature from room temperature to 600 degrees. And that also exhibits these 3 stability regimes. This one is captured by the transition from friction to flow, this rate and state to rate dependent mechanism. And this one is just a competition between 2 healing mechanisms. So this is a natural sample, so it's as good as it gets. And the third one is basalt, just to cover an oceanic lithosphere kind of context, also published last year. 3 different regimes of stability: strengthening, weakening, strengthening, and also evolution of the frictional properties with temperature softening at high temperature, which is basically the trademark of a mechanism here that is much more thermally activated than friction, and that means basically creep, right? So essentially, this is the universal behavior of most rocks, okay? So if they don't behave like this, we will have to really question why and question the equipment as well. But rocks behave like that, and that explains the transition from velocity weakening to strengthening as a function of velocity at constant temperature. transition from strengthening to weakening as a function of velocity, of temperature. So it's a two-dimensional space. And so that's how friction works. And now, as promised, I'm going to describe the thermobaric activation. So we've seen that stability depends on velocity, depends on temperature. And now we're going to add a third dimension to how these dependencies are affected by pressure, by confining pressure. And so going back to the friction law that describes nominally friction, but also the transition to flow by adding the contributions of viscoelastic processes and also frictional processes. And we remember that it depends on the activation energy and the activation temperature. But in fact, an Arrhenius activation like this one, it's been developed in the 19th century empirically, just fitting curves, has found later on a theoretical background that was developed in the 1930s, which is called absolute rate theory, that connects this to thermodynamics. And these parameters now take a different meaning. This is the activation enthalpy of the transformation, and the ratio of Q to T is the change of entropy of the reaction. So if you reorganize molecules, you change the degrees of freedom, and that gives you a different entropy. And in this context, we can extend this formulation to give it a pressure dependence. There's different ways of doing this. You know that an activation enthalpy has an internal energy contribution. This is one way. Another way is to look at the pressure dependence of the activation temperature. And so when I tackle any problem in science, I ask myself, what do I know about this that applies to this so I can make progress very quickly? And that's simply the Clapeyron slope of the transformation. Have you heard of this? Do you know what the Clapeyron slope is? So if you do geodynamics or deep seismology, you're looking at slabs going down in the earth, and you have the perovskite to post-perovskite transitions, and this is a function of temperature and pressure. And so this is a very classical thing in seismology. And so if a slab goes down and you have your anomalies going up or your anomalies going down, it refers to different Clapeyron slopes of transformation. That's a parenthesis. The point is that there is thermodynamics background for that, and simply telling you that the activation temperature is a function of pressure. Okay? And the slope of this is controlled by this parameter called the compressibility factor. That can be positive, it can be negative, but typically it's positive, greater than 1. Sorry, never negative. Ooh, no. It can be smaller than 1 or greater than 1, typically greater than 1. That describes the equation of state of non-ideal gases. Okay? That's what it is. If you plug this temperature dependence to that, you notice the exponential. You have the exponential of a log that becomes a power. And so that gives you normal stress to a power. Okay? So that's the flow law. It's modified to have a normal stress dependence. This term should really be inside of that, but by the magics of mathematics, it can come out of the exponential to become a power law. And we also inherit all of the normal stress dependence of this term due to the modulation of the area of contact. And that is enough to give us the third axis, temperature, slip rate, and normal stress dependence of the frictional properties. So there's different ways that this can happen. This is a plot of A minus B as a function of temperature and velocity for 4 different cases. So you can have this situation where if you increase pressure, this will shift the velocity weakening area to shallower depth, so lower temperatures. Or it can widen the seismogenic zone, widen it enormously, or it can do nothing. Okay? So these are different possibilities that are simply based on the Clapeyron slope, which is controlled by the compressibility factor and the power law exponent of these different things. Same thing applies to the top boundaries, but I don't have time to explain it. So I'm going to show you 3 different data sets that describe this quite thoroughly. First one was a data set produced by my group in collaborations with Zhangli in the China Earthquake Administration in Beijing, where we have been spending many weeks producing data. So it shows these typical plots of temperature and velocity and how A minus B maps out in this space. And you have these three different regimes of stability. But then we do that at different pressures. And so you can see that the velocity weakening has actually shifted up. It's a subtle effect, but it has done that. And a better way to show this is to show these A minus B regimes as a function of normal stress. And you can see that at low normal stress, it goes deep, and then at high normal stress, it goes up, and it also kind of weakens the weakening effect. And so you can imagine at higher temperature, it won't be even frictional anymore. You will bridge the brittle to flow transition because of the confining pressure. And so that's how the model performs. And so in this case, it basically captures a shift of the top and bottom temperatures of the velocity weakening domain. And this data is for Pelona schist, which is a typical rock at the basement of California that was basically underplated from the Farland plate subduction some 60 million years ago. The second one I want to show you is for hornblende. So this is a type of amphibole found typically in the subduction setting, so it's important to study on its own. But never hornblende is found on its own. Okay, it's just a key mineral that's part of a greater mineral assembly. And that's data that's been produced by Yu and Her, published in 2020. So you have these two plots. You have temperature and velocity, these three different stability regimes, but done at different normal stress, or velocity, sorry, different normal stress. So at a high normal stress, it becomes entirely velocity weakening. Okay, so what happens is that the velocity weakening domain has widened. You can also plot it as a function of normal stress, and then you can see the widening of the velocity weakening regime. So when that happens, that implies different dilatancy of different weakening mechanisms, of different deformation mechanisms. And the last two ones, so I showed you four, not just three, our data are not as complete, but are still compatible with the model that I described. This is lawsonite blue schist. This is typical rock that's found between 20 and 30 kilometer depth at subduction zones. And this one is clay minerals, montmorillonite, that's found in shallow depths of subduction zone. So you can see, again, three different stability regimes. And this is now plotted as a function of normal stress. And you have the opposite effect as for hornblende, where the velocity weakening domain shrinks as a function of increasing normal stress. So all different cases really are possible. This is a great data set also for clays that show a widening of the velocity weakening domain, but from the top instead of from the bottom. So basically, the more data we look at, the more we document all the different possible cases that describe different sensitivities of normal stress, different healing mechanisms, or different deformation mechanisms at different temperatures. Okay? So to conclude, I've shown you a model of friction. I basically explained to you how friction works, from simple to more complex or more thorough. And the data from the lab, the raw data, are quite complicated. It's really difficult to grasp without much experience. So it's complicated, but it appears to be tractable. There's hope to understand this complex system, and it seems to be tracked and explained fairly well by the combination of these two equations that together can explain the frictional and viscous properties of rocks from the surface of the Earth all the way to the asthenosphere by using different constitutive parameters along the way. And so this model explains many aspects of friction, the temperature, velocity, pressure effects. It does not include explicitly the effect of pore fluid pressure, so that's coming up next. And so it expands and unifies previous theories and observations and provides a pathway to better understanding earthquake faults because we now understand what the state variable actually is. It is related to the real area of contact, and that modulates porosity, permeability, electrical conductivity, acoustic transmissivity, light transmissivity, all things that we can measure independently of mechanics. And so that means that in the lab, where we try to predict things, and in nature, we can measure state, which is really a fundamental aspect of friction. We can measure it directly. And so I think that in the future, that will give us yet another tool that we can use to predict earthquakes or laboratory earthquakes and really understand the system much better. So I'll stop here, take any question. If we have time, I'm not sure if we do. We do? Okay.
Thank you, Sylvain. There's time for questions. Yep.
So I have two questions. Thank you for the very comprehensive talk. So one is about the normal source dependence of the yield strength.
Yeah.
So even assuming the normal source, even if we assume the linear dependence of the yield strength to normal dependence, we can show the in the RSC regime, we can show the apparent yield strength depends on the normal stress as far as I remember.
Yeah, the yield strength obviously depends on normal stress. That's what defines friction. What I'm saying is that it depends on it non-linearly. So a Coulomb friction law is a simplifying assumption. It's not entirely wrong. It's useful in many ways, but it's wrong in the sense it doesn't give you the right insight to the underlying mechanics. So if you care about understanding the natural causes of this frictional resistance, it's not the right way to approach it. But any complicated function can be linearized. And when you do that to friction, you get the Coulomb failure criterion. But it's not great. I mean, it's something that was developed 2 centuries ago. We should move on. Yeah.
Can we incorporate the gravity effect or something into your project?
Can we go where?
The diatancy hardening or something?
Oh, yeah. Eventually.
There's a question right here.
Yeah, so if we can measure state evolution during experiments, that's very good also because it means that you can open a fault and actually put back the contact.
Yeah.
And then it's possible to implement numerical models with rate and state, which is not the case right now. So I have you.
Okay, so all of these, rate and state, and this assumes a representative surface area that's averaged and homogenized. So we can't. This is not the right way to open a fault and close it in a theoretical way. So you'll have to really go into the physics of a single contact to do that.
But you can measure the state right when you put in contact.
You mean in the lab?
No, like in the lab or in numerical way.
Yeah.
Could you?
So one way to measure state is the opening. In fact, it's done routinely in some of your labs, right? So you have the dilatancy, and it's simply a measure of distance, right? And it opens, so typically it opens when it shears, and it compacts when it's in hiatus. So either completely static or moving very slowly. So that's measured routinely already. So yeah, it can already be incorporated. Yeah.
Thanks for the great talk. You said that pore pressure is a separate talk, but isn't it implicitly in the sigma bar?
Yeah, it is. But it turns out it has another effect. So the Terzaghi effect, the effective stress is sigma minus alpha p, is a mechanical effect of pore fluid pressure. But there is a chemical effect. And this chemical effect modulates healing, modulates the efficiency of flow, and that manifests itself in effective frictional properties that look very different. Dry granite, wet granite, one is completely velocity strengthening down to 800 degrees. I'm exaggerating. You put water in it, pressurize it, it becomes velocity weakening between 150 and 350. That's not in the Terzaghi effect. And so it changes the nature of the contact and the chemistry of the contact. And so thinking just about mechanics, it will not resolve this. So we need to take that explicitly. We need to understand it. We need to understand the chemistry.
So, thank you, Sylvain. So, if I understand well, you
sum up all different effects, and then you get your strain, your state variable
Yeah.
state, etc., etc. Okay, so now let's say I have a big piece of crust with lots of different minerals and lots of different stuff, and I add them up all together, and I homogenize all this, and I look at it from space within some.
Yeah, no, you don't do that. So don't homogenize the crust, okay? You could do that in the 70s, but you can't do this anymore.
Well,
So
my data is homogenizing the crust.
it's just looking at the surface,
Yeah.
but it's sensitive in different ways, as we both know, to different depths, right? So what the future will be, in the near future, will be, I know what the crust is made of, which is kind of a stretch, but okay. I assume what the crust is, and for every rock and pressure and temperature that is found at this depth or this region, I know the frictional properties because they're fully mapped in the lab. And they are captured in a physical model. And that at any area, any volume within the crust. And so we can predict what the crust will do. And then it will manifest itself by surface deformation, which you will see from space. And then you can do some science with that.
But at what scale? At what scale do you need to know what the crust is made of?
Well, Yoshi just gave a talk that you need to understand heterogeneities to understand four-shock sequences. So it depends on what question you're asking, right? So it's, yeah, so what do you care about? And then you probably know the answer better than me.
Yeah, many thanks for your talk. And I have two small questions. The first one is that you just now you give us a parameter like the pressability factor of the non-ideal gas.
Yeah.
And I don't get the gas is where it is.
Yeah, there's no gas.
Yeah.
So when you look at thermodynamics, it's typically laid out in terms of mixing in solution, but the same mathematic holds for solid solutions, so minerals. And so the nomenclature of this term is for the compressibility factor for non-ideal gas, but it applies to solid state material as well. So don't be fooled by the term, the name. The name is, it's just a trick, okay? It's just thermodynamic, and it's fitting other curves that we don't want to know about. But there's a lot of science behind this and a lot of assumptions like we do here, right? So it's not perfect.
We have three more questions, one by Roland, then Jean-Philippe, and then Chris.
Really quickly, in that multi-parameter space, is there a point where frictional heating becomes important?
Yeah.
Should be built into the
Yeah. So that's not a constitutive effect. It's a dynamic effect. But and you take any of these things, you take basalt at high temperature, or you take granite. You can see that at high temperature it becomes weak, and very weak very quickly, more than any other rate and state effect. It's a first order effect. And so if you have shear heating and temperature softening, you develop frictional instabilities. And the opposite is interesting too. If you have temperature hardening and shear heating, you will harden your cracks and they will seal faster. And so that tends to shift a crack-like rupture to a pulse-like and other, cool sort of dynamics. So temperature effects are important. And the key is to constrain them in the lab so we can see if they're relevant in nature or not. Yeah.
Yeah, so the theory is very nice, and it's impressive how you fit the experimental data. But there's one thing that I don't get exactly. You're assuming that the sliding velocity is proportional to the shear stress divided by some yield stress to some power
Yeah.
n, right?
Yeah.
So in effect, you have a ductile flow.
No. It's a power law, but it's not ductile at all.
Well, okay. Well,
Because you need an area,
it's a power law.
and you need a real area of contact. It means it's heavily damaged. So it has to be in a frictional regime for this to happen.
It's a non-linear flow.
Yes. No, very nonlinear. Power exponents are 60 on average. 60.
Because the issue is that how to reconcile that with the more Coulomb criterion, right?
Yeah. So if the power...
It's not an exponential function, it's still...
Yeah. But the exponential function is wrong because it predicts finite velocity at zero stress, which is ridiculous. So it cannot be an exponential without modification. If the power exponent is high, that means that there is a yield. That means there is a threshold. If the argument is greater than 1, it's going to become much greater than 1, right? Very quickly, because you raise to many powers. And so that means that this denominator is a yield strength. If the power exponent was 1, it would just be a prefactor. It would not have the meaning of a yield strength. But if the power exponent is high, it creates a threshold, and that provides the yield, the static sort of state. Doesn't mean really anything, but the equivalent of a static stress. But it's trivial if you look at the friction law. Where is it? I don't even remember. Is it here? Yeah. So if you invert this high power, you get this. You get mu is mu naught. And that's it. It's as simple as that. The rest is modulation.
Chris? Really nice talk. Thanks very much. I have 2 questions. One is going to take too long, so I'm going to skip. Well, we can argue later about
I'd love to do that. Yeah.
But the other is maybe simpler, and that is that for contact rejuvenation, it's rejuvenation.
Rejuvenation.
I don't understand why you take a random variable for it.
Yeah.
The contact, in your sense,
Yeah.
size or state is always going to be small.
Yeah.
So random to me sounds like it could be bigger.
Oh, yeah. So the first assumption is that when you randomly connect neighbors, they're going to be smaller than they will eventually be if you let them compress and flatten for 10 hours.
Sure, but when they reform, they're always smaller.
Yeah.
They're always younger.
Yeah. Well, it's kind of with foresight, you want this to be weakening, and so it's a little bit by design. But it could be generalized to something else. It provides the tools to make changes. For example, it could have a lower bound on grain size and things like that. Like you can design other things. Yeah.
Last question, Yoshi.
Since shear heating is accounted, how can you get high velocity friction exponent?
Yeah, of course. I may have a slide for this, or I deleted it. I probably deleted it. Yeah, sorry. Yeah, the weakening basically that we see at high temperature here. Oh yeah, I need to say that. Temperature can be the temperature of the crust, or can be the temperature, the instantaneous temperature during shear heating. So during an earthquake, you can basically navigate this whole field because you increase velocity. Oh, now your shear heating is efficient, so you increase the temperature, then you slow down, and then you come back up. So this is a dynamic field that friction experiences dynamically during an earthquake. And so if you go there, you weaken because you're hot. And you're hot because you're fast. And so if you plot the strength as a function of velocity, it will weaken. But velocity is not the controlling factor. It's temperature. But velocity is the underlying cause of shear heating. So strong weakening that Giulio Di Toro, famously summarized in his science papers, is basically meeting this domain dynamically by shear heating. So it explains that. It explains lubrication.
All right.
Yeah. Okay, thank you.
Thank you, Sylvain. We'll continue.
Sorry, we need to put this on because it's recorded. If you want.
Next up, Yihe Huang on the contribution of the coevolution of earthquakes and fault zones to the fault spectrum. Yihe, what's yours?
Okay, I cannot really move my mouse anymore. Is there like a... Do I need to use this one?
You could just say goodbye to that.
Yeah, I cannot move my mouse to... Okay. If you want to stand up and relax, this is a good time. So Anthony, I need your help. I cannot really move my mouse on the laptop here.
Is it because the remote?
It must be because
It's because of the of this.
Oh, this one. Okay, still it's
Do you
not
think?
moving. Okay, I have to use this now, maybe.
Yeah, seems like. I mean, if you unplug it, maybe this your keyboard, your pad
I
would
think
work.
this is good. Yeah, it's working.
Okay,
That's
yeah,
good.
microphone next.
So the microphone is fine? Great. All right. So I like giving the last talk of the day, because I can control when you're going for dinner. If my talk is really short, it means I'm really hungry. So today I'm just talking about like the contribution of the coevolution of earthquakes and fault zones to fault sleep spectrum. By the way, my name is Yihe. I'm from University of Michigan. So this has been like a central theme of our research group to understand this problem, because we know that the material properties should be changing over time close to the fault. So let's just get back to the original model. Like we usually think about earthquake cycles, we think about this kind of feedback between the stress and the frictional strength. So these are just some really classic models proposed like more than 40 years ago. And in these kind of models, the stress is kind of controlled when we have the earthquakes, and also the amount of the sleep is controlled by the stress budget on the fault. But if we think about this, we will see that the fault also starts deforming when we have these earthquakes. So those deformation of the outfault medium actually change the material properties of the rocks and also affect like the earthquake behaviors in the end. So what do I mean by the coevolution? So here, let's just think about like a fault. This is like a major fault, and it's surrounded by like a bunch of fractures here. And then we start having earthquakes. So we have these big ones, smaller ones, for the outfault medium. But then they start to damage this fault medium as well. So as the time goes by, we're going to start having like a more well-established structure over here. So with some more damaged segments and some less damaged segments. So then what happens next? What will be the next earthquake? Can they actually control where they occur or not? And so here, let's just assume that the more damaged segments are also where we have like more earthquakes nucleation later. So then we'll actually have this feedback between the fault zones, earthquakes, and then earthquakes, fault zones again. So they're going to evolving over time again and again. And the beauty of this particular problem is that we can observe them. So we can observe these fault structures over time. We can also observe like the earthquakes over time. So ideally, these two things should be coupled together in our simulations and also theoretical predictions. So let me just give you some snapshots of what is happening along the way first. And of course, we have a lot of support from the seismic observations. In particular, if you look at the earthquake catalogs, you can recognize that there is actually a concentration of small earthquakes for a certain length scale. So these are from the Southern California and Northern California catalogs. And this is like seismicity on all fault, as a function of distance from the major fault strengths. And for Southern California, it kind of stays constant for a while, but then it decays really fast, after tens of meters. And the same for Northern California, but you can see the characteristic length scale here for this power law is actually different. So for Southern California, it's a little bit larger than the Northern California case. And we kind of think that this is corresponding to the fault zone structure we can observe around major faults. Of course, this is a very simplified version, but we know that they're like tens of meters or hundreds of meters wide. And if we believe that, it's suggesting the Southern California case has a wider fault zone structure than the Northern California case. Okay, besides the spatial constraint, we also have a lot of temporal constraints from the seismic imaging studies. So this is like one of the recent papers about Ridgecrest. So if you look at this magnitude 7.1 main shock, we know that right after that main shock, there's a huge seismic wave velocity reduction for the stations really close to the main shock hypocenter. So this dV over V, which is usually ambient noise studies talk about the seismic wave velocity reductions, is up to 7% for this nearby fault station. And we can also look at the spatial map here, and you can see that Close to the fault, there is like 7%, and it kind of decays away from the fault. But still, on average, we have several percentage, of the velocity reduction here. And another feature is that, this seismic wave velocity also increases over time. And for ridge crest, it's kind of increased, really soon, like fast within 2 weeks after the earthquake, but it doesn't really go back to the previous velocity level. So if we look at the spatial map here, we can see there's some damage left actually after this main shock, even 2 weeks after. So it just means like the healing time here is short, but we still have some permanent damage, maybe permanent damage, that we cannot really see within the 2 weeks scale. But this is also dependent on, what kind of method you're using to observe the seismic velocity reductions or the healing. So this is another observation from Vidali et al., which was kind of like classic paper, talking about the seismic wave velocity changes for the deeper part of the crust. So the difference here is that this is from active surveys, and that one is from ambient noise. And you can see from this active survey results is that for landers, it seems the healing process actually occurs over years, for the deeper part of the crust. And also they infer that there could be another change, after the Hector Mine earthquake, and then the crust kind of starts healing again. So those are just demonstrating that these earthquake ruptures, they do damage the all-fault medium, and we can observe that from the seismic data analysis. And of course, this is also supported by the rupture simulations, for example. These are all the different kinds of dynamic rupture simulations that produce damage and also fractures after the cold seismic rupture propagation. And in order to do this, we need to assume some sort of plastic deformation. And that's why you can see the damage is kind of asymmetric. In these kind of models, they're yearly along the extensional side of the all-fault medium. And also for the Okubo et al., we can see the fractures kind of coalesce, and they form these kind of fracture networks. And demonstrated by Gabriel, we have like these particle speed velocity vibrations because of the generation of the fractures as well. And the largest, like perturbation of the speed velocity actually happens close to the rupture front, where we have a really strong growth of the all-fault shear stress. So all these things just talk about like we have these damage generated by the earthquake ruptures again and again, very effectively. So I think it's kind of finishing up this part of the figure. Like we know the earthquakes are generating these cold seismic damage. And then, think about like we have the damage, what would happen later? Well, theoretically, we know that there is a relationship between the critical nucleation length and also the shear modulus of the medium. So I think Yushi showed this equation already, which is the H star. And this figure just demonstrates like the schematic figure of what that means. So before this rupture propagation, we actually have this unstable region on the fault. And this region has to reach like critical size, which is twice LC here. So this twice LC is like the H star we're talking about here. And you can see that for real estate friction, we have the AD parameters, effective normal stress, D or DRS. But here we also have the shear modulus. It just means that when you have a smaller shear modulus, you have a smaller H star. So it's actually easier to nucleate earthquakes, when you're inside this particular structure. And we actually calculated like how much this nucleation size can reduce when we have like a low velocity structure as a function of the shear velocity inside this structure, and also as a function of the damage zone width. So you can see that as the shear velocity decreases, and also as this fault zone gets wider and wider, we are seeing a reduction of the nucleation size. And for this case, is like about 40%, if we go from like 100 meter to like about 500 meter fault zones. So that's all we know from the theoretical studies. But how about if we put this relationship to earthquake cycle simulations? Is that really simple that we are going to see all the earthquakes inside the damage zones? So it's not really that simple. So here is just showing earthquake cycle simulations with some pre-existing fault zone structure, like a low velocity structure. And the difference between these 4 simulations is that the damage zone actually ends at a different depth. So here we have a really shallow fault zone, like the light blue color here is 6 kilometer. And now we're going to 8 kilometer, 10 and 12 kilometer right here. So you can see that when the fault zone is very shallow, because the fault is loaded from below, we're going to have a lot of stress concentration close to where we have this transition from a velocity weakening friction to velocity strengthening friction. And then we still see most of the earthquakes are actually below this damaged structure. But then if we go to this 8 kilometer or 10 kilometer case, we can see the earthquakes tend to occur close to this material interface, or they occur inside the fault damage zone. So this is kind of similar to the theoretical prediction. And also they have this kind of bimodal distribution where you have concentration of seismicity for the shallow and deeper part of the fault. So this is like observed somewhere like in California. But it's not like just the low wave velocity that is making effect. The previous simulation is a purely elastic simulation. And here, let's just think about if we have viscoplasticity, which is needed if you want to have damage, that could be even more complicated. So this is from the Mia et al. Paper, which is talking about like when you have this viscoplastic deformation over the earthquake cycle, you can actually have this redistribution of the stresses. So here you can see that you tend to have the partial ruptures, and these are kind of limited by the plastic deformation of the outflow medium. And as a result, you're going to have like these variation of the hypocenter locations as well compared to the elastic model. All right, so then, just think about this again. We have all these snapshots like from seismic data, from theoretical calculations, and also from simulations that kind of support we should have something like this over earthquake cycles. But then the question is, can we actually couple all these effects together? Can we allow this fault to damage over time? And can we allow these earthquakes to evolve over time and see how they are actually changing each other? So that's what I'm going to talk about next, which is what we are trying to do right now is to incorporate this continuum damage rheology into fully dynamic earthquake cycle simulations. So just to talk about like what we mean by earthquake cycles here, we're just talking about like these different stages, of the earthquake before and afterwards. So before that, we have this interseismic period, which can last for several years or tens of years, where you have this locked patch surrounded by the creeping region. And then we also have this preparation stage, like the nucleation stage, lasts for months or days before the earthquake. And then this is the earthquake time in which we have this rupture propagation and ground motion generated in the simulations. Of course, afterwards, we also have this post-seismic stage, which kind of redistribute the stress and allow these faults to heal over time. So that's what we mean by earthquake cycles. And to do that with the damage rheology, we have to add a few more equations into our earthquake cycle framework. Okay, so here I'm showing the most important equations for the damage rheology. We are actually preparing a manuscript, which I promise will have more than 20 equations over there. But here is showing like what is really most important. When we think about this, we can think about this like a plastic deformation. So we are going to have awful plastic deformation that is kind of damaged. But then what's different from the plastic deformation is that it gives a feedback to the elastic properties of the outflow rocks. And how do we give that feedback? It's from these equations here. So here, the first one is the damage accumulation rate. And you can see that it only happens, when we start having the plastic deformation. So when this strain kind of overcomes the threshold. And it is determined by this CD parameter, which is slip rate dependent. So it just means that for cold seismic period, we should have a faster accumulation rate compared to the interseismic period. And this can be quantified from the laboratory experiments. And then, this alpha dot, which is damage accumulation rate, is also affecting how much plastic strain is accumulating over time. So these two equations are the most important, during the cold seismic stage. And then during the interseismic stage, we also allow this alpha to change over time based on a logarithmic heating law. And in all these stages, this alpha will actually control how the shear modulus changes over time, because this is an anti-prim problem, so we only care about how shear modulus changes. And this is like the initial shear modulus, and this is the maximum shear modulus reduction for the system, and this is alpha. So you can see like it's naturally giving you the co-seismic damage and interseismic healing over time. And here is just the model setup again. We're having this anti-plane problem. So here you can see where the fault is, and this is more like a vertical strike slip fault and a cross section showing how like the shear happens. And here is showing the unfold friction. So we have this AB parameter again. I know like Sylvain showed all these fantastic friction, but we're still using the most simple friction laws to reproduce the earthquake cycles. But this A minus B parameter, you can see that still it's like a velocity weakening for the upper 15 kilometer, and then it's strengthening afterwards. And we don't really have a velocity strengthening friction for the shallow part. And the reason for that is because we want to demonstrate while you have the damage, you are actually going to have some natural shallow slip deficit without any velocity strengthening friction. And then this is like the effective normal stress gradient with depth, which is 10 megapascal per kilometer. So it's kind of assuming that we have some overpressure along the fault. Well, for the out fault, we also need to define the stresses, because we have the plastic deformation, the damage, and we're actually using the same stress as the effective normal stress on the fault. So this red line here is just like the mean stress for the out fault medium. And this is an important parameter because it's defining the yielding strength of the system. So here is showing like the yielding criteria or the yielding strength, ICR2, and you can see that it's increasing with depth. And this is kind of natural in these kind of simulations because it's kind of harder for the deeper part of the fault to yield. So let's start from just some simple simulations, which is like starting from a homogeneous medium, and we're just comparing what is different when we introduce this damage rheology. And for these kind of figures, the red lines show the co-seismic slip for every 2 seconds, and the blue lines show the interseismic slip for every 30 years. And the stars show the hypocenter. So this is like a cumulative slip of 90 meters. Well, if you look at it from whether it's far or close, you don't really see much difference, right? So like they actually look pretty similar in terms of how much co-seismic slip is released on average. But what is different is actually close to the surface. So close to the surface, this is where we have a lot of damage. And you can look at this kind of blue lines, right here. And you can see that over time, there seems to be like a net, long-term shallow slip deficit in these kind of damage rheology models. This is just because the deformation is taken by the outfold medium instead of the onfold. And also for earthquake, the co-seismic slip also has like a reduction close to the surface in the damage rheology models. So this is kind of separate from like the long-term shallow slip deficit. And this is like the damage distribution along the fault for a homogeneous simulation. So this is the alpha parameter, which kind of shows the color and contours. And here, if we define like the damage is the alpha larger than 0.001, you can see most of the damage is actually shallower than 1.5 kilometer for this simulation. If you plot the plastic strain, you can see that equivalent plastic strain can actually penetrate to the deeper part of the fault. So these two are not like equivalent to each other. But as I said, those are from like a simple homogeneous setup. If we think about this, we will realize that this is not a simple homogeneous medium even to start with. These kind of damage is evolving, and we do have some pre-existing damage close to the fault already to begin with. So that's what we are going to do next. We're going to include some pre-existing damage into these simulations, And this is just like a simple initial rigidity reduction in the all-fault medium. And we prescribe like different percentage of the rigidity reduction. So here just comparing like a 40% initial rigidity reduction with like a no rigidity reduction. So again, if we look at these kind of figures, overall the co-seismicity is not very different. But when we have more pre-existing damage or like a higher initial rigidity reduction, we are going to see more and more shallow slip deficit for the shallow part of the fault. And what is like more different here is actually the distribution of the damage. So this is the previous elastic strain figure, and this is the one with a pre-existing damage. So you can see like if we use 10 to minus 4 as like a criterion here, for the pre-existing damage case, we're going to allow this damage to penetrate to the deeper part of the fault. So as a result, this fault damage zone can be actually deeper over time than the previous case. And we are also seeing like a richer behaviors of the earthquake, like the seismicity, distribution, and also like the dV over V, like what we see from the seismic imaging studies. So here we just use different initial rigidity reduction to start with, and then we plot like where the earthquakes are in terms of their hypocenter depth. So you can see that if we have like 10%, 20% rigidity reduction, we are actually having both shallow earthquakes and deeper earthquakes in the simulations. But then for 30% and 40% reduction, we actually see a deepening of the earthquakes. So the earthquakes tend to occur like in the deeper part of the crust. So then we're just going to take this damage we see from the cycle simulations, like after 5,000 years, and then mirror this change of the velocity. Okay, so for this one, this is just like a co-seismic. So this is not like over 5,000 years yet. So this is like only co-seismic velocity change, like the similar dV over V as we see from the seismic imaging studies. And we plot these, as a function of like the different earthquakes we see. And this is what we see from, our simulations for the shallow part. So you can see after each earthquake, there is a reduction or like an increase of dV over V. And then it heals over time, which is pretty quick in this kind of scenarios. But we also see that there is correspondence between like the dV over V we observe and the initial damage we have in the simulations. So when we have like a higher initial rigidity reduction, we tend to see like a higher dV over V in these kind of simulations as well. And we can also, check what is the relation between the earthquake depths and the dV over V in our simulations. So this is just another figure plotting the hypocenter depth as a function of dV over V we observe from each earthquake. So then what we see here is that there is actually a depth dependency for earthquakes deeper than 10 kilometers or so. So you can see there is some sort of transition of this dV over V over this particular depth range. So why is that? We can actually plot, the damage or the dV over V for each earthquake in like one setup of the simulation. So for example, here for 20%, we can see there are both deeper earthquakes and shallow earthquakes. And we're going to plot the co-seismic damage for the shallow and deep earthquakes and see how they are distributed. So this is, for the shallow ones, and you can see because they are really shallow, the rupture propagation doesn't really change the damage or affect the distribution of the dV over V that much. But then for the deeper events like these two, because the rupture propagates through this whole velocity weakening fault, so they actually generate enough damage that affect the dV over V that we observe from the surface. So there is a correlation between how deep the earthquakes are and the dV over V we are observing from the seismic imaging studies. Well, another question that people usually talk about is how much of the damage really comes from the co-seismic period and how much damage comes from the interseismic period. And here, because we're assuming this damage accumulation rate is a function of the sleep rate, so we definitely see a lot of the damage is happening in the cold seismic period. So this is just showing like within, this from this triangle to the star here, this is only like 1.5 seconds, and we can see like this huge jump of the dV over V for the near surface area. And also this is showing like what is happening during the interseismic period, and we can see that this is right after the earthquake, and this is 25% of the earthquake cycle. So most of the damage is actually healed, for the very early part of the post-seismic period. But then, this magenta color shows the damage distribution right before the next earthquake, and we're seeing that there is actually some damage close to the surface. So it means like the damage rate actually exceeds the healing rate for the surface here, which can be considered as some sort of precursory damage close to the surface. Okay, I know I don't have enough time, but I think this is really interesting results if we think about another parameter space here, which is actually the strength of the fault. So I just showed like the damage, but now if we think about the maturity fault, they also have like maybe different strengths. So this is like we're sitting here all day and we wind down, we just lose the energy. We got weaker maybe. So this is like showing the faults are also getting weaker as they mature. And we change the friction coefficient, from 0.6 to 0.2 here. And this is for the same pre-existing damage. And you can see that when we change this to a weak fault zone, we're going to see a very complicated seismicity distribution. So we have the foreshocks, like migration and the main shock, and also aftershocks here. And also we see that there is a dependency on the magnitudes distribution in our simulations as we change the strength of this fault zone structure and also the pre-existing damage. So both of these are for a weak fault zone, but this is like a less pre-existing damage than this one. And you can see that as we increase the pre-existing damage, we are seeing like more earthquakes between this magnitude 4 and magnitude 5 range. And this also shows like the temporal behavior of the earthquake magnitudes. And you can see like for this particular case, before the large earthquake, we see like more earthquakes with similar magnitudes. So it's more like a swarm-like behavior, for the foreshock migration in these kind of simulations. And another important thing from the simulations is that we can see the damage. So for the previous case, we see this kind of flower structure. But if we have a weak fault zone, the cold seismic damage is not necessarily like this flower structure. It's because we have all these small and moderate earthquakes, bursting for the deeper part of the fault. So you can see that for this particular time, we actually see like these isolated patches of damage for the deeper part of the fault. Okay, so the last slide is just showing that there's some sort of anti-correlation between the earthquake magnitudes and the damage we're seeing as well. So what we are calculating is a mean damage variable. This is just taking the spatial mean of the alpha and plot that as a function of the magnitudes. So for larger earthquakes, they should rupture a larger area, so they should have a larger damaged area as well. But if you average this alpha, you can see it's actually smaller than like the smaller magnitude earthquakes here. And this anti-correlation is even more stronger like when we go to the more pre-existing damage case. Okay, so this is just to summarize. We do see that there is a lot of interplay between the stress and the materials over the earthquake cycles. And when we incorporate this damage rheology, we are going to naturally have more long-term shallow slip deficit, like development of the fault zone with the cold seismic damage, interseismic healing, and maybe some precursory velocity change. And also we have this complex seismicity evolution for the weak fault zone case. And also for the damage distribution, we see the flower structure from this strong fault zone a lot. But for weak fault zones, the cold seismic damage can actually be very isolated and deep than the flower structure. So that's it. Thank you.
Comparison between the change and damage, I think the important thing is for the parameterization constrain those parameters from the low experiment or low data experiment thing, or the default 1B measurements can help to constrain those parameters. Like since that in the closed world, if we observe the 4% of decrease, and then we can parameterize those things, and which way is better to really constrain your model to the compared to nature.
So are you trying to say that should we better constrain these parameters using the laboratory data or using the more observation data, field data? Yeah. So I think, still like the parameter space we are choosing here are based on the laboratory data. It's just because, they are much better controlled. Like we know this is caused by the damage, right? So we can know like what is the sleep rate dependence, what is the right order of the magnitudes we should choose. And I think the difficulty for field data is that, we have to be able to just attribute that to the damage effect. But that's what we are trying to understand here. Yeah. Yeah.
Very interesting talk. I was wondering, so you showed this case where you make the damage zone rheology weak with effective friction coefficient of 0.2.
Right.
So what would happen if the damage zone is weak and it's also weakening, and that's the effect of the accumulation of damage, while the main fault is made strong? Could you have a dynamic effect hosted in volume and have an earthquake without the main fault structure?
So great. So basically you are saying if we set up on-fault friction 0.6, off-fault 0.2, something like that?
So it's a question that in my mind relates also to, because you're using continuum rheology to model really a discrete collection of discrete subsidiary faults and fractures, etc.
Right.
So, well, in this recent work that we did with Alice, we had cascades. So we model explicitly faults within the damage zone, subsidiary ones, and we could have an earthquake realized as a cascade on a network of subsidiary faults without the main fault ever rupturing. So in that model, this continuum damage representation of the fault zone is something similar possible.
Yeah. Well, yes, I think, like basically what we are doing now is to project like all these off-fault seismicity like deformation to like the damage we're seeing here. So they may actually be earthquakes, occurring on the secondary fault fractures that are causing the deformation. But I think what you're saying is that, if just earthquakes are in the off-fault medium, but nothing on the off-fault medium, is that even possible in these kind of simulations? Is that right?
A large earthquake in the damage zone.
Yeah. I think.
Alice, question.
Thank you for a fantastic talk. I think this is super timely, really interesting results. I just have a small question. Did you see any strain localization in your models? I'm wondering why there's no, in the plots you showed, why there's never any localization. Did you choose your stressing in that way? I'm just, because this is something you really.
So what do you mean by strain localization? You mean like temporally? There is a. Spatially?
It just looks very smooth to me. In the dynamic objects you're running with these kind of rheologies, it's pretty easy to get shear bands for the localization of strain. I'm just curious.
Yeah, so I don't think like we see like what you were saying, because I think I saw like your students, rupture simulations during Slovakia, which was having this kind of localization, like shear bands.
Not just our.
Yeah, well, I don't think, we see that here. So, I mean, are we implementing like the exactly same continuum damage rheology? This is a fully dynamic simulation.
But there's a viscous regularization in the damage well base.
Right.
We kind of stay away from ill-post situations. Good question.
There's the way you model the damage. So you're changing the modulus, and but in rocks, it's the role of microcracks and fracture is a way more like intricate than this. You have hysteresis effects. You have also the way you convert damage to wave speeds. You have frequency effects as well. You have the static stress change that produces some kind of effective modulus, but what you sense with the wave speeds can be fairly different from that. So I wonder if there's any opportunity for for this type of like complexity, and it's not complexity for the sake of complexity. It's actually first order things that you observe in the lab. If there's provision to use these more like with a realistic damage laws, to put it this way. Because the signature in the wave speed can be dramatically different if you use like static versus dynamic effects and things like this. Is it easy to? I mean, easy, I guess no, but like, is there a provision to investigate those things?
Right. Of course, I want to talk to you like about how to choose like the right, rheology, like, right models. But I would say like for these kind of simulations, the hardest part is to make the numerical simulations converge. So when you add more complexities, they just tend to blow out. Like we don't want to converge anymore. So this is why we choose the continuum damage rheology. It's just like a, continuum, like a smooth version of what you observe from the lab. So it's,
And I think the original version is even more complicated. It's the Liachowski and Benzyme version.
Right.
You have simplified it to implement it. There's time for one more question, and then we have to move to the lightning talks.
So I was wondering, when you run multiple earthquake cycle simulation, do you see an evolution in the characteristic of the earthquake with time as the fault mature? Because maybe you showed it, but it was not super clear to me. So like the first earthquake and the last one, how different they are?
You mean like in terms of sleep distribution, or in terms of like
the characteristic of the earthquake evolve as the fault matures?
Yeah. So I would say like for the strong fault case is very simple, right? But if you go to the weak fault zone case, of course, they change a lot over time. And it really depends on how long you run this earthquake cycle simulations. So here it's showing like 10,000 time steps, but we actually run this like to three times of this particular thing. And we can see that, initially we have these small moderate magnitudes for the deeper part of the fault more, and large earthquakes for the shallow part of the fault. But later in the cycle, we actually see sometimes the deeper part of the fault happens like more larger events, but then the smaller ones are shallower. So there's definitely like a variability for the weak fault zone case.